Independence of two events means that the outcome of one event does not influence the probability of the other. With our new notation for conditional probabilities, we can now formalize this definition. Events A and B are independent whenever the probability of B given A is equal to the probability of B. Equivalently, events A and B are independent whenever probability of A given B is equal to the probability of A. Let's look at a contingency table that classifies a random sample of patients at a hospital by blood type and sex. Are being blood type O and being female independent events? So, according to our formula, we have the probability of the type O given they're female should equal the probability that they're type O. So there's 107 type O females divided by 225 females. And it's equal to, or should be equal to, 183 over 390, which is the probability of selecting somebody with type O. As you can see, these fractions do not equal. So therefore they are not independent events. If they were equal, they would be considered independent events. Another way you could do this is look at the probability of type O and female, and it should equal the probability of type O times the probability of female. So we have 107 type O females out of 390, and it should equal the probability of a type O, which is 183 over 390, times the probability of a female, which is 225 over 390, multiplying these two together, and you can see they do not equal. So this is another way you could prove that they're independent or not. Disjoint events cannot be independent. Well, why not? Since we know that disjoint events have no outcomes in common, knowing that one occurred means the other didn't. Thus, the probability of the second occurring changed based on our knowledge that the first occurred. It follows then that the two events are not independent. A common error is to treat disjoint events as if they were independent and apply the multiplication rule for independent events. Don't make that mistake. It's much easier to think about independent events than to deal with conditional probabilities. It seems that most people's natural intuition for probabilities break down when it comes to conditional probabilities. Don't fall into this trap. Whenever you see probabilities multiplied together, stop and ask whether you think they are really independent. Sampling without replacement means that once one individual is drawn, it doesn't go back into the pool. We often sample without replacement, which doesn't matter too much when you're dealing with a large population. However, when drawing from a small population, we need to take note and adjust probabilities accordingly. Drawing without replacement is just another instance of working with conditional probabilities. A tree diagram helps us think through conditional probabilities by showing sequences of events as paths that look like branches of a tree. Making a tree diagram for situations with conditional probabilities is consistent with our make a picture mantra. Here's a nice example of a tree diagram and shows how we multiply the probabilities of the branches together. So you can see that we have a first event, whether they binge, drink, are moderate drinkers, or abstain. And then the second event is, have they had an accident or not? Reversing the conditioning of two events is rarely intuitive. Suppose we want to know the probability of A given B, but we know only the probability of A, the probability of B, and the probability of B given A. We also know the probability of A and B, since the probability of A and B equals the probability of A times the probability of B given A. From this information, we can find the probability of A given B. So the probability of A given B is equal to the probability of A and B divided by the probability of B, which is the same thing as the probability of both occurring, divided by the probability of the given. This is called Bayes' rule. Let's take an example. 3.3% of the population are infected with a certain disease. There is a test for the disease, however, the test is not completely accurate. 94% of those who have the disease will test positive. However, 4.4% of those who do not have the disease will also test positive, called a false positive. What is the probability that any given person will test positive? So let's look at a tree diagram. We have our first event, whether you're infected or not infected. You can see that 3.3% of the population are infected. That means that 96.7% are not infected. Now we create two branches from this, and this is where the test tells you whether you test positive or negative. Those infected test positive 94% of the time. That means that 6% test negative. Those not infected test positive 4.4% of the time, which means that 95.6% of the time they test negative. We want to find the probability that any given person will test positive. The probability that you test positive is equal to the probability that you're infected and positive plus the probability that you're not infected and positive. The probability that you're infected and positive is 0.033 times 0.94. The probability that you're not infected and positive is 0.967 times 0.044. So multiplying and adding, we get 0.074. What is the probability that a person tested positive will be infected? So this is kind of a reverse of what was given. So we're looking at the probability that you're infected given that you tested positive, which is equal to the probability that you're infected and positive divided by the probability that you're positive. The probability that you're infected and positive is 0.033 times 0.94. The probability that you're positive we found earlier, which was 0.074. So multiplying and dividing, we get 0.422. So what can go wrong? Don't use a simple probability rule where a general rule is appropriate. Don't assume that two events are independent or disjoint without checking that they are. Don't find probabilities for samples drawn without replacement as if they had been drawn with replacement. Don't reverse conditioning naively. And don't confuse disjoint with independent. So what have we learned? We now know the general addition rule and the general multiplication rule. We also know that conditional probabilities and that reversing the condition can give surprising results. Venn diagrams, tables, and tree diagrams help organize our thinking about probabilities. We now know more about independence. A sound understanding of independence will be important throughout the rest of this course.